Hello, this is Shinichiro Horikawa, and this is the 26th episode for VEX for Algorithmic Design, and the topic for today is about the recursive basics. And this is the outline for today's sessions. I'm going to start by explaining what is recursion, and then show you 3 ways to implement this recursion in Houdini. One is for each loop, one is using a solver, and one is just use VEX. Then I'm going to show you several examples for the recursion. One is Sierpinski triangles and tree with Dale systems. And in the last, I'm going to show you how you can implement subdivisions using the idea of recursion. When you go to a Wikipedia for the recursion, you'll be able to see its general definitions, saying recursion occurs when a thing is defined in terms of itself, its type. Recursion is used in a variety of disciplines, and mostly used in mathematics and computer science. And this is what we were talking about in this session, since we're going to use this for algorithmic design. It is all for mathematics and computer science. Now you might ask, what does it mean by a thing is defined in terms of itself or if of its type? In mathematics or computer science, it can be explained like this. Having a function called fx equal to 1 plus fx plus 1. Here you can see that if fx is the function, which returns the value adding 1 and the another functions inside its functions with the different parameter. Looking at these equations carefully, you can see that the same function f is being used as the return value with the different parameter x or x plus 1. By doing this one, you can actually have another return value which contains this same f from the right hand side function value. As a result, you'll be, for the second line that's showing, this fx plus 1 can be converted into 1 plus fx plus 2. Okay? And this fx plus 2 can be then converted into 1 plus fx plus 3. Just like this, recursion in computer science or mathematics can be expressed like this. You can have its own function as the return value and repeatedly do the same operations over and over again within the functions. Just like calling yourself repeatedly again and again. And that is the process of recursion in terms of mathematics and computer science. Now there are a variety of usage for this recursion, and one of the popular usage for this recursion techniques is to create a fractal pattern. Now one of the property that fractal has is its own self-similarity. When you close up to the pattern, you can see the same pattern when you were looking from far back, like with a big image. And by using recursion techniques, you'll be able to create this fractal pattern pretty easily. And one of the example I'm showing here is the one called Koch curve, which act like this. First you have this horizontal line, then you divide the line into 3, split it into 3 lines. And from the center line, we're going to create this equilateral triangle, meaning all the edge shares the same length, and remove the center line. This is the end of the process for the first iteration, and this operation, or you can call function, can operate on a single straight line. And in the next iterations, you have these 4 single lines connected like a curve. And you can actually operate the same process that you have done for the first iterations for each curve, for each line, like this. Split the line into 2 and into 3, then create a equilateral triangles like this, and remove the center line for each line. And as a result, you'll be able to create this a fractal curve. And you can continuously operate on each of the newly created lines to make it smaller and smaller for a detail, for those line detail. And the shape of this overall fractal pattern and its own component shares the same shape. And that is the fractal pattern, and that's how you can use recursion to create this kind of pattern. And if you want to do things like this using a programming language like C, you do like this. First, you create a function. In this case, I'm naming the function as test. You also define some parameters you want to use inside a function. You do any kind of operations. And that is actually the end of the process for the first iterations. And after everything is done, what you can do in order to do the recursion, you call its function, the parent function itself, and return it as a value. Okay, in this case, I'm returning the same test function that I have defined right here. As a result, the same function called again. Now, when n starts from 1, n becomes 2 in this line, and then the parameter that's going to be inside this test will be equal to 2, right here. Now in the next iteration, the same function will going to be called, and the parameter that you are going to have is equal to 2, and the next iterations you have n plus 1, so n becomes 3. Then in the next iterations, another test function will be called with the parameter 3, and so on, and n will be incremented by 1 at each process, each recursive process. In this case, infinitely. I said infinitely, so if you want to stop at some point, you have to create some conditions. When do you want to stop this infinite process? Now that's how the recursion works inside a programming language normally. Although in Houdini, since we are talking about the VEX language, and the VEX language is still based on C, but runs on multiple objects simultaneously, unfortunately, we cannot create a recursive function like this shown in an image. What we cannot do is to have its own function inside the function, like this. So we have to know the other way to implement this kind of recursion in Houdini. So I'm going to start by explaining what kind of implementation you can do for Houdini to do this kind of recursion, to create a geometry like fractal pattern. Mainly, there are 3 ways to implement a recursion inside Houdini. Now in Houdini, there's mainly 3 ways to implement recursion. One is to use ForEach feedback loop, which is going to be the easiest to implement. Another way is to use the solver, which you want to use it when you want to create a recursive animation. And the difficulty using this solver is pretty similar to when you use the ForEach feedback loop. And you can also use only VEX to implement the recursion, which is going to be the most difficult way to implement. So most of the time I would prefer using ForEach feedback loop or solver to implement the recursions, and avoid using just VEX using wrangles. But I'm still going to show you how you can do that in these sessions to see what's the differences. Now in this topic, what I'm going to show is to create a simple, really simple recursive geometry, which is going to be the spiral curve shape, with the following process. First, I'm going to define a single point on somewhere on the space, then define its moving direction, and move the points toward that direction in a second step. Then in the third step, I'm going to rotate its point using the initial position as a rotational axis with some angle. And in step 4, I'm going to move the point upward, in this case y-axis. And finally, in the last step, I'm going to connect the initial point position with the last point positions to create a line. Now I'm going to continue operating this process for the last point positions. So in the next iterations, I'm going to use this last point positions as the initial positions from here, from the step 1. Then move it spirally. Okay, so this is what I'm going to do as a basic spiral, basic recursion practice using 3 different techniques. One is to use the ForEach feedback loop, one is to use the solver, and one is just using VEX. So let's see how we can do that starting from a ForEach feedback loop. Now let's see how we can use ForEach feedback loop first to create a spiral recursive curve. Now I'm going to go inside the geometry node, and first thing I'd like to do is to create initial point positions to start off the recursion. So I'm going to start by creating a single point in the space, maybe starting from 0, 0, 0. So create an add node to first create a single point at the 0, 0, 0 positions. Okay. Then I'm also going to define the direction in which direction I want these points to move. So first of all, I would like to move this point in X direction. So I'm going to create a attribute create node to define the attribute called direction, or I'm just gonna call this there, as a point vector value going into the X direction by 1. Now since I want to operate the same function over and over again to the last point, only to the last point, I'm also going to create a group to define which point is the last point. So I'm going to create a group node, and let's name this, let's call this point type, and let's call this last. Now everything is set, we can start creating a feedback loop. So I'm gonna start by first creating a for each. In this case, I would use a number. Most of the time, when I want to do the feedback loop, I use this for each number. But any for each type can be used, but probably using for each number is more suitable for the feedback loop. So I'm gonna use this one. Bring it right here and connect the point to the first input of this for each loop. Now it's the time to convert this for each node, for each loop into a feedback loop. Now currently as a default value, it is not set as a feedback loop, but what it does is once it operates for the first iterations and the next step, you use the same input coming from the input initial input and do the same operation to the same geometry over and over again, just like the normal for loop in VEX. Now if you want to do the recursion, what you want to have is the last updated point position or last updated process. In this case, once we move the point, this one, to somewhere, then we want to use that last positions to operate the another function, another same functions from that point, for that point. To do that, we have to modify some settings for this for each loop in order to be able to use the lastly moved point as the next input, as a next parameter using the same function. You can assume that this whole set can be one single function which can be used as a recursion. Now to do this, first you click this for each end node and change the gather method to feedback each iterations. And another thing you need to do is to click this for each begin and change the method to fetch feedback. With these combination, having a feedback each iterations for the gather method and having fetch feedback as a method for the for each begin, you'll be able to convert this loop as a feedback loop. Now as a result, what you do inside this for each loop as a process will be repeatedly done for the lastly updated geometry. So let's see what I mean by that. If you don't want to use the code, you can try using something like transform. I'm just gonna test with the transform first and go using the VEX code later. So let's say I want to transfer this point to a x direction by 1. Such as I have just moved this point to the x direction, and what I would like to do next is to merge the old point with a new point. And I want to have this group called last only for the new one, newly translated one. And I also want to translate only the point which have this last group. So for the transform, I'm gonna set this group type to point and set it to last, so that this transform only acts for the point with the last group. Now, for the previous one, I want to actually delete the group called last. So I'm going to use the delete group delete. Okay, now in this first loop, I have created 2 points. One is the initial points, and one is the updated last point. Okay, and by connecting the merged result to this one, to the ForEach end, and activating the ForEach end, you'll be able to see in total 1024. Now that is pretty big. The reason is because we have to only pick up the last point for this step in order to move the point. So instead of setting this group last as a filter for the transform, I'm going to just pick one single point using nodes like delete, and just pick the group which has the group called last for the points. So then only the point which have the last group will be moved, and in this case there's only one point that has been moved using this one. Now I think I need to say delete non-selected to pick just one point. Okay, as a result, and visually it looks just the same, but in total, now I think I need to activate this. Now one thing I forgot to do is when I use the group delete, I have to define which group to delete, and I have to delete this last from the point group. Okay, and let's check again. Now here is the point which starts from the first point, moving to the x direction at each iterations for the last point. And if we look at the point number, we only have 11 points. So at each iterations, the point and the last point has been picked and moved to the x direction by 1. And you can change the number of iterations right here in the ForEach end by changing the slider. So when there is no loop iterations, the single point stays at the same positions. If we have just one iterations, then the last point has been moved to the x direction by 1. If we go 2, we have 2 points moved to the x direction, and so on. So this is the basic idea for recursive using a ForEach feedback loop. And let's try to also rotate this point using this 0, 0, 0 position, which is the initial position, as the rotation center, and move it upward as well to create a spiral trail using these transform without using the VEX first. So to do that, after we have moved this point to a x direction, we can have another transform. Now in this case, let me change this to the first, just show the first iterations, so that we can see how it works. Now after we have moved the point to the first to the direction with 1, I'm going to rotate it maybe using a y-axis, using the center as a pivot by 30 degrees. Okay. And after rotating this point, the next thing I would like to do is to move the point upward to the y direction. So I'm going to give another transform node. You can just do it in one single transform, but just to make it clear, I'm separating this transform node. Then let's move the point upward, let's say by 1 as well, or maybe 0.5 in this case. And this is going to be the final step for this first iteration, this single iterations. And then combine with the old points, which you can now have this trail connect and can later be connected with the line. Now that we have created this single process, and if we continue doing this for the last point using the same process, let's see what happens. If we increase the iterations, you can see that the point starts to rotate, move the same direction, x direction, rotate it 30 degrees and going up. You can start to see this kind of spiral shape happening. And as a result, you'll be able to see a bunch of points arraying like a spiral curve. Now, if you want to connect this as a spiral curve, then you can use something like add node for those list of points and change go to the polygon tab, go to the by group, and you'll be able to create this spiral curve by connecting all those points. Now in the last, I'm going to resample this to make it smoother by changing the street polygon as subdivision curve, then use something like poly wire to have a thickened value. Like this. Easy as it is. By changing these iterations, you can change the length of the spiral curve and so on. So this itself is the recursive process that I've just implemented using ForEach feedback loop and without any code. Now let's also try to do the same thing, create the same geometry using the same feedback loop, but instead of using transform node, I'm going to try to use the VEX wrangle node, since we are inside this VEX for algorithmic design session. So I'm going to copy the whole set to the right hand side. I'm going to modify the process which is inside of ForEach loop. I'm going to start by deleting all the node here. Now instead of having all those nodes, I'm just going to use a single wrangle node to process all the stuff I did using a transform node and group delete and so on. Okay. Now what I'm going to do here, let's first name this create spiral recursively. And let's filter the group and to define which point should be using this code that we're going to write here. So that is the point which has this last group. The first thing we want to define is how much you want to move in a x direction and how much you want to rotate as an angle. So let's try to have that as a parameter. So for the length, how much you want to move, I'm going to name it as step length 2x. And you also want to move it on y direction as well, so let's also have that parameter as well. Step length x and step length y. and step angle. Let's promote these, and let's set the same parameter like we did for the last time. So move into x direction by 1, move to y direction by 0.5. For the angle, I'm gonna say 30 as a degrees. Okay, so let's start by trying to move this point to the x direction. So first of all, what we're going to do is to bring up the current point position from the point which is inside this last group. So vector positions is actually the at p itself, so you can just say at p as well. Now what I'm going to do is to update this point position, pause, and move it to the x direction. And the x direction can be written hard-coded, or you can also refer to the attribute that I have created for each of the point, which has this directional attribute. So if we look at the directional attribute, we have this 1, 0, 0. So actually we can use this one to move the point to x direction. So let's go back and say position, update the point position by a direction, multiply by step length x. Now I have just moved the point to the x direction, point position to the x direction, but currently no point has actually been moved. But in order to move the point or to create the point, you have to actually update the point position or just create a new position by using a function like add point. Since we want to leave the original point coming from the first input, what I'm going to do here is to add a new point. So new point is equal to add point, and the first one will always be 0. And as for the second input, I have to type a point position which I want to add the point to. Now, next thing you need to do is to define the group called last for the current new point. And also you want to remove the last group from the last point, which comes from this at p. So let's do that as well. I'm going to, first of all, set the last group to this new point by using the function called set point group. And the name of the group that I want to have is this last at new point. Now, I have to say 1 in order to add it to the group. Now, if you want to remove the last point, which is going to be this one, the previous point from the last group, then you have to say set point group 0 last, and the current point number is at pt num. And if you want to remove it, you have to say 0. And that's it. Now, as a result, you'll be able to have the point added to the previous point being moved to the x direction. Then the previous point will be losing the last group. The new point will be inside the last group. And in the next iterations, you can use that last point with those group to move to the same direction over and over again repeatedly. Now let's see. Now I'm just seeing 2 points right here, but I do see a number of points being iterated. So I think there's still some problem here. I think if I look at the geometry spreadsheet for the point, now the newly created point doesn't have this directional a vector value, so that was the problem. So we also have to define this directional value to its point in order to move it. in the next iterations. So let's also do that. Going back to the code, we are going to, let's see, somewhere around here, set point attrib 0, and let's call direction, and to the new point with a new directional value. And in this case, I'm just going to copy the direction from the previous point. That's it. Now all the points start to move into x direction one by one using the last point. Now let's also do the rotation and moving to the y direction as well. So just like we did, after we have moved the position to the directional x direction, we're going to rotate this by 30 degrees by using this angle from the parameter. So in order to rotate, what we were using is this rotational matrix. So first I'm going to create a rotational identity matrix by saying matrix mat is equal to ident. Then create the rotational matrix by rotating this matrix by a angle, this one. But in order to rotate, you have to convert this from degrees to radians. So I'm going to use the radians functions to convert this angle from degrees to radians. Then we also need to set the axis, the rotational axis. Now in this case, we want to use the y-axis as a rotational axis, so 0, 1, 0 as a vector. Now that the rotational matrix has been created, we can now rotate the positions by multiplying rotational matrix and update the position. Okay, as a result, at each iteration, the point has been rotated 30 degrees like this, and start to create this kind of a circular motion. And by moving the point upward and the last, you'll be able to create a spiral point trail. So let's move the point upward by adding a set 0, 1, 0, which is the unit vector for the y direction, and multiply by the step length y, which you have defined how much you want to move to y direction at each step. Now, as a result, you get a similar result like you did with a transform, like this. And by increasing the iterations, you'll be able to have a bunch of points at and on top of a spiral position. Now, if you activate this polywire, you'll be able to see the same result like this. So it might be a good idea to use the wrangle instead of using a bunch of transform node. One reason is because this is going to be faster, because you're not using like separate operations, multiple operations separately, and also this is acting multi-threaded. This also probably acting multi-threaded for each node, but since you have multiple nodes, you lose some effectivity or performances a little bit. And it might be easier to see what it does with those bunch of nodes visually, but when it gets really complex, then it might start to make sense to pack it as a single wrangle node. What it actually does inside the code is pretty much the same like this one. And since you can set those parameters as a slider in one place, I think it will be much easier to manage the operation. The next thing I would like to talk about is how you can use the solver to do the recursion instead of using the ForEach feedback loop. Now let's see how we can do that. First thing first, I am going to reuse some of the setup that I did, which is those initial setup to create the first point, set the directional attribute, then create the group. So I'm going to bring up, copy all those 3 nodes and start with this to use to create the recursion using the solver. Now the benefit of using a solver for the recursion is that you can actually create an animation how this recursion activates or iterates over time. If you use a for each feedback loop, then what you get is the instant result of the last process. But by using a solver, you can iteratively see what happens during the process, during the iterations. And you can see each step in each frame. So if you're into something like motion graphics, you want to show the recursive animation over time, then the solver is the way to go. And the difficulty using the solver, it's pretty much the same as the for each feedback loop. Now what you need to do, first you need to bring up the solver. And actually we have already used the solver for the feedback or the recursion purpose, because solver itself is a feedback loop. And in other sessions for this series, I have already talked about the basics of solver, and in that session I've also explained how you can use a solver to create a feedback loop, creating some kind of fractal-like pattern. So it is going to be the rephrasing, but let's see how we can do the same thing that we did that we did right here. Now inside the solver, what we need to do is to define similar things that we did right here inside a for each feedback loop. And actually the great thing about this is that we can just actually copy those code which is inside this feedback loop as it is and paste it inside the solver. So I'm going to copy this create spiral recursively point wrangle, which have all these code, and paste it inside the solver. Now the input that we're going to get from this prev frame is the one that's coming from the last frame, which is similar to a for each feedback loop with the feedback option. So in the second or third iterations, what you get from this for each begin is actually the last processed step, the last processed result coming from the last for each end. So it's looping like a cycle, updating the geometry over and over again. It's doing the same with this solver. So what you need, in order to use this, what you just need to do is to connect this prev frame to this same create spiral recursively point wrangle, and that's just it. And don't forget to activate the last node, which is going to be the output for the next step. Now if you go outside the solver and play the animation, you start to see the same result but with an animation. Each step the point will be created like this, and moved X direction, moved Y direction, rotated 30 degrees, and continuously doing it over and over again for the point which has the last group. And if you try to copy these 3 nodes and connect it this solver, you get exactly the same result but with an animation like this. Pretty simple. So once you be able to create the feedback loop recursive using the feedback loop, it's pretty easy to go for the animation by converting this feedback loop into a solver, because you just need to use the same wrangle, same node setup, which is inside the feedback loop. You can also bring these set of group, set of node to the solver as well in order to create the same step. So you can consider that these 2 types of implementation for recursion can be considered as a set. If you can create one, then you can also create another one pretty easily, pretty fast, because it's just copy and paste. Now the next thing I'm going to talk about is how you can actually use only VEX to do the same thing, the same recursion, which is the most difficult way to do the recursion in Houdini. Now let's see how we can do this. It would be a good idea if we could reuse some of the code that we write previously. So let's copy some of the code that we have written previously. So what I want to do, first would like to copy all those three first initial setup, which is pretty much the same, and also copy this node, the point wrangle node, which is inside this ForEach feedback loop. Okay, bring it right here. Now the method that I'm going to show is pretty similar to what we have done for the ForEach feedback loop, but instead of using the feedback loop like these, I am going to just write the additional for loop inside this code instead of these one, and use it as a feedback loop. And that's the method. That's how you can implement the recursion just using VEX. And there are some tips to do that, so I'm going to show you how you can do this. Now currently there is no loop, so only one point has been moved using this create spiral recursively point wrangle node. Only a single point has been created, moving point to X direction, rotated 30 degrees, and moved upward by 0.5. Now in order to create a feedback loop like this, what we need to do is to create a for loop to cover all these processes. So thinking as these as a single function, and then what we want to do is to repeat this function over and over again. So what I'm going to do is to cover all these, wrap all these process as a function, and put it inside a for loop with some iterations. So I'm going to define how many numbers of iterations I'm going to have. I'm going to create a parameter like num iteration, then use that to define how many loops I want, like this, and then bring up the parameter, promote the parameter. Let's say I want to repeat 10 times. Now currently the single point has been moved, the initial point position has been moved to the same direction over and over again, so we still have 11 points, but all the points comes to the same positions. What we want to do is by moving the point in the first step, we only want to move the last point using the same process like this one. Now to do that, we have to have some values to be bring up as a updated value in the next loop, in the next iterations for this loop, and that value has to be the point position of this last point. And if we look at those value, if you look at the variables, some of the variables written here, the positions that we're talking about is actually this value. And currently what we're doing here is that in each iterations we are resetting the point positions to the current point, and in this case the current point here means this last point. So we actually don't want to do that. We don't want to reset the point position to the same initial point positions, but we want to update this position over and over again at each iterations by considering adding a new directional vectors, directional values to it, rotation, and moving upward, and so on. So to do it, we're going to first bring this outside the loop, so that only once the point is going to move I mean, only once the point is going to refer to the original point positions, which has this last group. Now, just by doing it, if we look at the result, you already see the result that we wanted. And if we try to increase the number of iterations, you can actually already create the point which is moving and which is creating this spiral curve. The difference between the feedback loop and this one is that at each iterations we no longer use this last group like for this one, because what we are referring to is just this last positions, so we actually don't really need this last group to be set for each newly created point, because last group only works if we want to separate the process, because it's being used to filter which point you want to do the operation for these movement and rotation and another movement. But in this case, we already know which point we want to move, which is this position vector variable. So we don't actually need to filter it. We already know what variable to move, so we can just delete those group related function and it just still works fine. Now it starts to make more confusing if you start to create some branches out of those points, maybe creating another spiral from each of the points, so that you can have like a tree-like shape. Now in that case, using just the VEX code gets really difficult, but I'm also going to show you how you can do that with some example later. But overall, this is how you can use only VEX to implement the feedback loop. I mean the recursion. Now, as a final touch-up, I'm going to copy all these to create a spiral curve as a geometry. Alright, let's go to the next one. As a simple practice to create a recursion related geometry, I'm going to start by creating this shape called the Sierpinski Triangle, which is one type of fractal shape starting from a single triangle. And if you do the operations, what it does is to separate or split the triangle into 4. You have 3 filled triangles on the side and 1 empty triangle on the center. Okay, and the next process will be activated for those filled triangle with the same process. Now you have 3 triangles for each side over again. So that's what I would like to try to implement using Houdini with all 3 method: ForEach Loop, Solver, and VEX only. So I'm going to start by using a ForEach loop, ForEach feedback loop, to create this Sierpinski triangle shape. And as an initial setup, what we need to do is to create a single triangle shape. So let's do that first. I'm going to start by creating a circle node, and let's place it on XZ plane, and let's set it as a polygon with the 3 division, so that you'll be able to easily create this triangle shape like this one. And since this is reversely flipped, I'm going to flip this. Doesn't really matter if you want to do it or not. Okay, now this is going to be the initial profile that I'm going to use in order to create a fractal shape, a Sierpinski triangle. So let's try to operate on this triangle to create a fractal shape. So what we wanted to do is to split this triangle into four divided triangle. One on the center is empty space, and one on the side is a filled triangle. And this operation only works for the filled triangle shape. So let's try to do this. Now, before getting into the code directly, let's think about what's the easiest way to do the single operations to split these triangle into four. In this case, 3 filled triangle and 1 empty triangle. So let me first create a for loop for each number. And if it's possible, it's always a good idea to start by using just a transform node or node that's available from Houdini without using wrangle, if it's possible. If it's not possible, then you can directly go with the wrangle. But most of the case, if it's possible, it might be a good idea to create a prototype using these kind of a simple node to do the operation that we want. Now in this case, what I can think of in order to create a 3 separated or splitted triangle, 3 filled splitted triangles, what I could think of is to first get this triangle with the point as a pivot. So let's say one of the vertex of this triangle can be pivot, let's say this point, and using this point I can scale this triangle as a half size, and as a result what we can get is this triangle at the edge. And this triangle actually is the triangle that we want to have as a side triangle, split it into 3 filled shape. Now using the same process and using the same concept for each vertex, we can do the same scaling as a half size. So if we use this pivot to scale, then we can create the triangle on the upper side. If we use this right hand side vertex as the scaling pivot, then we'll be able to have a triangle, the half size triangles on the right hand side. And as a result, if we repeat the same process for all those 3 vertices, we'll be able to have this 3 half size triangle, which is the one that we actually want it. As a result, to have a 3 splitted triangle. And on the center, you have this negative space, which is another triangle. So let's try to do that using only this transform node. Let's see how we can do this. So first thing first, what we want to have is the point position from a single triangle. So to do that, what we can do, the thing is that in the end of the loop we have multiple triangles, so we have to pick each triangle one by one. So what we're going to do, if we just want to use this transform node and no vex, then what we can do is to use the ForEach primitive to access each of the triangle one by one. So we have this double loop, nested loop like this, and the loop inside this feedback loop is the one in order to access each triangle shape one by one. And for each triangle shape, what we want to do is to retrieve 3 point positions, and we know that this triangle only have this 3 points, so we can actually get each point by saying delete or maybe we can actually access to each of the point by having another for loop for each loop, which in this case for each point. So it starts to get a bit complex, like this. So in this second loop, we were accessing to each of the triangle. And on the third loop, we were accessing to each of the point for each triangle. So in result, this loop always has this 3 iterations in total. Now that we have each point in each iterations, we want to use that point as a pivot pivot positions, and use it together with this transform to scale the triangle. And the triangle that we want to modify is the one coming from this second feedback loop. So I'm going to connect this triangle to a transform right here. And inside this transform node, we can define where the pivot is for the scaling inside this pivot transform. And by setting the position right here, we'll be able to set where we want to scale it from. Now in the default, it is set as 0, 0, 0, but what we want to do is to use the point for coming from each iterations in this loop as a pivot positions. So in order to access that information, I'm going to create a null node in between the third loop, let's say pivot. And then I'm going to use some expressions inside a transform node to access to this point position of this pivot. So to do that, I'm going to access to the attribute called P. So the expression that I'm going to write for all the X, Y, and Z is going to be something like this. Point pivot, and the second input is the point number, and there's only one point at each loop, so I can just say 0. And the one that I want to access is P, and then I want to access to the first index is going to be the X value, so 0. So this is the X value for from the pivot point, and we can copy and paste for the Y and Z and just replace the last value to 1 and 2 to access the corresponding coordinate. And using this pivot, what I want to do is to scale the triangle by half size, like this. So currently the pivot is right here, so the triangle has been scaled using this pivot to make it a right-hand side triangle. Now, as a result, what I want to do is to, since we want to have 3 triangles using this third loop, which has 3 iterations, we're going to replace this output with this one. It looks a bit confusing, but if we get out of the loop, we'll be able to create 3 primitives like this. If we look at it, we have 3 polygons, 3 primitives being created. And if we also leave the loop with the feedback iterations, and I actually forgot to set it as a feedback loop. Let me change this to 3 iterations. So the gather method feedback each iteration is fine. We also need to change this for each begin and change this to fetch feedback. As a result, you'll be able to see the one that we wanted to have. So a fractal shape, a Sierpinski triangle. So if we change these iterations starting from 0, 1, 2, 3, you can see that it is actually working. So if you just want to use the transform node and all those node without any wrangle, then this is the way to go. Now the downside of it is that, as you can see, it has to have a lot of an inner nested loop like this, makes it really confusing to look at. So in this kind of cases, if we want to have a multiple branches happening at each iterations for the next feedback, I would start suggesting use a VEX wrangle instead of creating like these, which is still understandable at this moment, but it's starting to get more messier if the geometry becomes more complex. Now if you overlook what we have done here, the first loop is the feedback loop, just like we did created for the first basic example. And in the second from loop, what we want to have is accessing to each of the primitive, because we want to create a 3 triangle from each triangle, okay, multiplying the number. Okay, so if we only have 1 triangle in the first iterations, then we can create a 3 triangles in the next iterations. If we have 3 triangles in the next iterations, then what we want to have is 3 by 3 in the next iterations, meaning as a result we have 9 triangles. In the next iterations, we are going to have 3 from each triangle, so 9 multiplied by 3, we're going to have 27 triangles, and the number will increase vastly over time. Okay, and this second loop is accessing to each of the triangle by using the ForEach primitive. Now for each primitive, you have 3 points, and you want to use that 3 points to scale the triangle using those points as a pivot. So I am having another for loop to access each of the points from the triangle and use that as a pivot with the transform node like this. Now this is the prototype to actually create the feedback loop to create a Sierpinski triangles, and I'm gonna use this. I'm gonna refer to this structure and try to implement this same thing using VEX instead of having all those nested loops. So what I'm gonna do is to first copy all those setup and just delete the one inside the feedback loop. I'm gonna replace it with a wrangle. So in this case, I want to access each of the primitive, so we can actually use the one called primitive wrangle. And the benefit of using this primitive wrangle, it acts simultaneously, like it for each primitive, it runs parallel. The process that you write here runs parallel for each primitive, compared to the one that have here. For if you use the for each primitive, the process runs one by one linearly, so the process is going to be much slower than using the primitive wrangle. So that's another benefit using wrangles instead of this feedback loop for loop for inside the feedback loop for the recursion. I think that's it's going to be the big benefit of using wrangle. If you have tons of iterations, if the geometry is really complex, and we can actually check that by calculating the time later. I mean the processing time. Now let's rename this to Sierpinski Triangle. Let's try to do what I did right here. Okay, so the first thing I would like to do is to get all the pivot point positions from each triangle, and we can access to each of the point by using a function called prim points. So let's use that first for each primitive. As a result, in all the cases, since we are only dealing with the triangle shape, the total number of this point coming from the primitive is always equals to 3. Now, in order to access each of the point, we can do the similar thing for this third nested loop by creating a for loop to access each of the point. So int I starting from 0 and use the length of the points to define how many loops I want. Then inside the loop we can first access to the point position. So first get the point number from the PTS array, get the point position using the point function 0 accessing to the P attribute, which is the point position at each point number. Now I want to use this point position as a pivot to scale the triangle. And in order to do the scaling inside the VEX, what we need to do is to modify the triangle point positions. Okay, so we need to access all those 3 points. Oops, forgot to say why. We need to access all those 3 point positions from this triangle inside here. So we need to have another nested loop here to access all the triangle point position, which is pretty much is the same that we have here. So I'm gonna copy all these set, paste it. So now I have nested loop. I need to change this variable, so I'm gonna change this to n. And let's also change the name of the variable. So I'm gonna name it as npos. Now, using this position as a pivot, I want to move this triangle point position. In this case, I'm going to use the scaling process to move this point positions. So to do that, in order to use this point position as the pivot, what we need to do first is to move this triangle point position by its point pivot positions. Do the subtraction like this. Then from that point, we can now do the scaling by just multiplying by some numbers. So let's say we want to multiply by 0.5. Okay, and after we have scale the position, we have to bring this back to the original positions. So what we want to do, bring back by adding the pivot position again. So making a sandwich like these. First subtract with the pivot, do the transformation, and bring back to the original point position, the original pivot positions. You always do like this. Same for the rotation. If you want to use this point position as a rotational axis, then you do the same thing like these. Okay, as a result, the triangle position has been updated by scaling by 0.5, and I want to use all those 3 points that has been processed inside this loop to create a new triangle. So what I'm going to do is to before get it into the loop, I'm going to create a triangle primitive, starting with the empty vertex. Just set the type as a polygon. Then inside the loop, I'm going to add the vertex iteratively. So using add vertex 0, and to the triangle primitive, I'm going to add this point. Now I also need to add the new point position, new point geometry or a new point number in order to add it as a vertex. So I also need to add a new point using add point function at npos, which is the scale positions, and bring this new point as a new vertex for this triangle primitive. Now last of all, after we have done all these setup, you'll be able to create, by using this loop, we have 3 loops using this points. So actually what we can have is 3 triangles being created using this loop. Now after creating the 3 triangles on the side, right here, we don't really need the original triangles on the center, which was the 2 times bigger one. So at the last, we can say remove primitive, remove prim 0, the current primitive, and we are left out with 3 splitted failed triangle. Now I think I have some errors here, so let's see. I forgot to set the comma. Okay, so like this. Starting from the 0 iterations, in the first iterations, I have successfully divided the triangles into 3 by moving by scaling each triangle from each of the vertex by 0.5. And in the next iterations, I'm doing the same operations for each primitive, scaling from each of the side by 0.5, and so on. And you can you'll be able to create this Sierpinski triangle. And you can kind of see some variations by modifying some of the parameters that you have set for this one. For example, I'm multiplying by 0.5 to make it half size, but what if I change this to something like 0.25? It still works, but the result you get is something different. So in the first iterations, you get a 0.25 scaled triangle, which is on the side, which no longer has its connections on the edge. Now in the next iterations, it becomes much smaller, creating like these triangles and so on. So you can play out with changing some of the parameters to see how it actually works. If you make it bigger, like 7.7, you start to see a bunch of triangles nested to each other. Maybe in this case, showing it as a wireframe might make sense. Like these. So just modifying those parameters can create some interesting geometry, I assume. So try out with that. Now that we have implemented this Sierpinski triangle with the ForEach feedback loop together with the VEX, let's also try to convert it into use the solver to do the recursion. Now, as I said, using the solver is easy if you already have this ForEach feedback loop. So first you have the solver. Let's also bring the initial setup copied and connecting like this. And what you just need to do is to do the same process inside the solver instead of the feedback loop. So I'm gonna copy this node that I have created and then go to the solver, paste it, connect it, activate it, and if I play it, you can easily create this fractal animated. Although as you can see, small number of iterations can create a vast number of geometry. Like if I go to like iterations 11, it already have so many numbers of triangles already. If I look at the number of primitives, I already have like more than like 10,000 or 100,000 numbers of triangles, 177,000 triangles. So if I keep playing timeline, then I think it's just going to crash with not enough of memory of this computer. So in order to reduce the speed, how fast it creates the iteration or it process, in some cases, if you want to use the solver with these kind of vastly growing fractal shape, what I often do is to reduce the step. Like once in 10 step, just do the iterations and so on, so that I can have 100 frames to operate for 10 iterations. Okay, so let's try to do that as well for this solver, which is not that hard to do inside a solver. I'm just going to use the one called switch node and create a condition that only, and connect it like this. So the previous frame comes to the first input of the switch. The second input will be this triangulated or splitted triangle. And the second input will only be activated if the current step, current frame is the multiplication of 10 or 20. So let's say, and to do that we write some expressions. So $f is the current frame number, an integer, and if we do the remain calculations using modulus, maybe by 20, and if it's equal to 0, then that's the timing when this select input becomes 1, and otherwise it's keep at 0. So starting from the frame 1, let me just reset this feedback loop. So starting from 0, frame 1, the select input keeps it as 0 until it comes to 20. When it becomes 20, then the select input becomes 1, and that's the first timing when this be activated. And from the frame 21, it'll start to become 0 again. So by doing like this, you'll be able to slow down the iterations, the animation, by each 20, so that each iteration will be activated, each process will be activated for each 20 frame, like this. Which I think is a necessary technique if you want to use the solver together with this recursive operations, especially if you have a branching like these triangles, which can create a vast number of geometries with the single iterations. The next thing I would like to do is to try to create this Sierpinski triangle only by using VEX. And this is the part when it becomes really hard to do, when it becomes really difficult to do. So most of the time I would suggest, if you want to use the if you want to create the recursions, I would suggest using either solver or feedback loop together with the VEX. And don't go for only VEX method, because that's going to be really complex to understand what is going on, and it's also going to be hard to understand. It's going to be hard to implement. But as a practice, I'm still going to show you how you can do that. So let's do this. First, as an initial setup, I can just copy this single triangle as a starting point. And I could also copy this primitive wrangle right here. Now this single wrangle will create a single step. Now I think I'm seeing the cache as well. Let me go back to the top. Okay. Now it's going to be a lot more complex than the one we did in the basic session, creating a spiral like these. Previously, we were just using a for loop to wrap the functions to do the feedback loop, but when you have a multiple branching happening, like having multiple numbers of geometry created at each iterations, it's going to be much more complex if we want to use this only wrangle method. One of the reason why it's so difficult is because the VEX doesn't have a structure called nested array, meaning you can only have one-dimensional array. So that's one of the reason it's going to be really difficult to create a recursive just using one wrangle. Another reason is because of this process, how it creates the geometry. Like if you try to create the geometry procedurally using a function like add_prim or add_point, you cannot actually use the result point number or primitive number for the other function which works on point or primitive, such as the function like primPoints only works if the primitive has already been created on the previous frame or on the previous node. This primPoints cannot be used for a primitive procedurally created inside the same node. So let's say you have just created the triangle primitive right here, and this triangle primitive right here, this tree prim, it defines the ID or the primitive number of the newly created triangle right here. But within this wrangle, you cannot use this number together with this primPoints to get its point numbers. You have to first leave the wrangle, then use the primPoints to actually get the points information from this triangle primitive number. Because of this, it makes it really hard to create the recursions just inside one code. And the final reason why it's so difficult is because of the limitation that you cannot really create the function inside a function, call the function inside a function, just like I told you in the first basic explanation. That's pretty much the same for all the others, but that's the three big limitations it has, so which makes it really complex to do the recursions in one single node. And there's also one big downside, because if you try to do this whole setup in one single node, then you cannot actually run the process simultaneously on different triangles in this case, but you have to iteratively do the process one by one to each of the triangle linearly, which makes the process pretty slow. And this total speed of this calculation will be similar to the one that is right here, which is looping one by one for each step. So compared to this one with this one, using the primitive wrangle to access all the triangles simultaneously for each step, or the solver, this process is going to be slower. So there's no meaning using this method. It's complex, it's too complex, it's too slow. Why use it? But just for study, you still might want to know how it's going to be, how you can be implemented. But in real practice, I think you should avoid using this process. So if you're not interested in those, you can skip this part. Now, first thing I would like to do is to wrap all these functions with the for loop, just like I did for the spiral. Okay, so I am going to cover all these with defining the number of iterations. Let's have t as a variable, and create a parameter like number of iteration. Wrap all those functions. Like this. Now we need to modify some of the part. One thing I would like to modify is this remove prim, the position of this remove primitive. In the last time, I would like to create this triangle iteratively divided, split it. But since I'm just accessing to this single triangle, and that's the only primitive that I'm going to get out of this at primnum. So I don't have to put it in the loop, but I can just put it outside the loop so that I can just delete triangle, the base triangle one time, and that's pretty much it for the removal. Okay, another thing I would like to do is to move this functions, getting the 3 points out of the primnum triangle, primnum. Since, as I said, there's only one triangle starting from the first input, and add prim can only access to its single primitive. So I'm going to move this to the outside the loop and bring it like these. So this is going to be the initial point numbers. The next thing I need to do is that as I said, after I have created the geometry procedurally, if I try to create a geometry procedurally, then you no longer be able to use those point number or primitive number for the operations such as these movement as well, transformation as well. So what I would like to do at this point is to convert all those point numbers into a point positions. So in that case, we can use those vector values to feedback at each loop. If we have this point number, then we cannot use it for the feedback loop within a single node, a single wrangle VEX code. So what I'm going to do is to create a vector array by converting each of the point number into a positions and append it inside this vector array. So I'm going to create a array called positions for the vector, starting from empty array and accessing to each of the point. In this case, we only have 3 points from single primitive. Getting the point position out of the point number. At PDSI, and then append this position into a positions vector array like this. So now I have just created the vector array which have 3 points from a single triangle, 3 point positions out of 3 triangle, out of 1 triangle. Now next step I need to do is to go fix some of the stuff which is using add prim or add point. We actually don't really want to use this add prim or add point inside a feedback loop because it will just create the geometry with the point number or primitive number which cannot be used for the next iterations. So instead, we're just going to bring the updated positions stored inside the array and use that array for the feedback loop instead of using those primitive number or point numbers. So I'm going to disable this add prim or add point, all the stuff which is doing the procedural geometry creations, and left out with all the vector transformation. We cannot really use this one as well, and this one as well. So using this point function is also not available because we are considering that we don't have these point numbers, but instead we have this positions. So we have to replace this point numbers into a point positions. So let's change this to positions. Okay, and actually the number of positions or number of iterations what we want to do for these for loop is fixed to 3 because we're dealing with a triangle. So we can just say 3 instead of the length of positions. And this loop only acts for a single triangle, but actually there's a chance that in the second or third iterations we have multiple number of triangles. So to deal with all those triangles, we need to have another loop accessing to each of the triangle. And if we go back to the first things that I did, I'm talking about this second nested loop. I currently have this feedback loop, which is this for int t equal to 0 and so on, the number of iterations. That's equivalent to this outside feedback loop. And the one that I have here inside for int I is equal to 0 and I is less than 3 is equivalent to this third nested loop. So we can see that we are missing this second nested loop, which is accessing each of the triangles. So that's what we need to implement as a code. And to do that, okay, well, I think we can convert this into 3 as well. Now to create the second nested loop, we'll create a loop somewhere around here in between the t and I. So let's call this int for int s equal to 0, and s is a, so in this case we have to do the loop by a number of triangles. We actually don't have the number of triangles right now, so let's just assume that assume there's a variable called num3 which have the number of triangles, and do the loop and covers these loop. Wrap this loop up like this. Okay, now we need to define how many triangles are there currently, and we can assume how many numbers of triangles are there by getting the number of the current positions and divide it by 3. Initially, we only have 3 points inside a positions array, so if you divide it by 3, then you get 1, which is the number of triangles. If we have 3 point positions inside this array, then that means if we divide it by 3, then there's the result is 3, so that means we have 3 triangles explaining or showing inside this vector array. So int num3, the number of triangle, can be determined by first of all getting the number of positions which is stored in the array, then divided by 3, and that is actually the number of triangle. Now after having all these after setting all these nested loop, so the first loop is the feedback loop, and the second loop is the accessing to each of the primitive, in this case triangle, and for each triangle I'm accessing to each of the point. Okay, now what we need to do is to get the corresponding point position out of the positions array. Instead of using like PTs go to PTS and vector pass point function, we're going to get the positions from this positions array. Now to get the positions, we need to define the index. Now the index can be defined by, first of all, multiplying s by 3, which defines which triangles we're accessing to. If the s is equal to 0, then which means we're accessing to the first triangle. If s is equal to 1, then we're accessing to the second triangle. Then, since there are 3 different points for each triangle, I will add I, which corresponds to the index of each point for each triangle. So if s is equal to 0, then this whole index will be equivalent to 0, 1, 2. Okay. If s is equal to 1, then the number will be 3, 4, 5. Okay. So this 3 numbers will indicate the positions for the triangle vertices. And you can create index like this. Now that I have this point position information, let me delete this. The next thing I would like to do is to going into this loop to do the scaling by setting the pivot position as well. And currently we are also missing this pivot positions right here. So do the same thing that I did here. So I'm going to copy this one and name this to n, which is going to be acted as a pivot positions from the positions array. And instead of using I, I'm going to use n because we are using n variable here. As a result, you have just scaled this positions n positions by 0.5. Actually, this position was the pivot, and this n pos was the position that I wanted to transform. So sorry for that. So this is the pivot position. This is the one that I'm using to transform. Now, previously, after I have created this positions for a new triangle, I was using this add prim to create a new primitive, but we cannot really do that in a single loop, a single wrangle, because as I said, we cannot refer to this primitive number or point number in the next feedback loop iteration. So instead, what I'm going to do is to create a new array storing all those newly created positions. So in this case, I'm going to create a vector array somewhere inside, right after the new iterations for the feedback has been begun, named as something like vector new positions with an empty array. Instead of creating a triangle primitive, I am going to add this new positions to this new positions array by saying append new positions with n pos. So by doing this, after leaving all those nested loop, you'll be able to have this new position filled with the set of 3 points for each triangles, for each newly created triangles. So if you have one triangle, and right here, if the num triangle is equal to 1, then in the last you'll be able to have 3 triangles, meaning 3 points for each triangle, so 3.3, which is equal to 9 points. So inside the new positions, you are having 9 vector values as a positions. And what I want to do next is to, in the next feedback iterations, after after all those processes, I want to bring this new positions used as a new positions to calculate the next triangle like scaling. To do that, I can do that by replacing the current positions with this new positions, like positions equal to new positions. By doing it, in the next iteration, right here, the num of the triangle will become to 3 because now the positions have 3 by 3, so 9 points. So if you divide it by 3, you have 3 triangles. Okay, and if you do the same, and now you can do the same process like this, and for each 3 triangles, you can, and for each 3 points, you do the same process. And in the last, the new positions will have a 27 points. And this 27 points will be used in the next iterations, and the number of triangles that you can get is equal to 9. And so on. Then it continues like that. So in the last, you'll be able to have a bunch of vector positions which is stored inside this positions after you leave this feedback loop. Now, at this moment, this is just the array of vectors, so no geometry is shown. So the last thing you need to do is to use this informations, the vector array informations, to convert it into a geometry. To do that, you do a similar things. First of all, you determine how many number of triangles are there inside this positions. So you can do that by calculating the same thing I did here. So first get the number of triangles by dividing the length of positions by 3. Then create the loop using this number of triangles, just like I did right here. So like this. And you also want to access each of the point to get the point positions and create it as a triangle. So I'm going to do the same. I'm going to have the same loop. I is equal to I at 0 and until is less than 3. Okay, and after the first loop, I'm going to create a triangle primitive. I can do that because I can do it here because I don't really need to refer to this one in the feedback loop. This is not a feedback loop. This is just to accessing all the triangles. So I can do it right here. Add prim 0 poly. And then inside this feedback, inside this loop where I try to access the point positions, I can access it by using the same index as multiplied by 3 plus I, which is going to be the point position for each triangle. And this time I can add a new point by saying add point 0 at positions. Now I can use the add vertex to add the point to this triangle primitive number. So 0, 3, and pt. And as a result, you'll be able to get the triangle. Now this is currently I have this number of iterations as 0, so let's promote this integer, and if I try to increase this value, I can see that it's working as I supposed. So as you can see, this is much more complex than using all the other method, which could be interesting as a puzzle to understand how it really works. It's pretty similar to what I have done right here, but as I said, this is too complex and also slow, so I wouldn't suggest using this one, but instead I would suggest using this method or this method using VEX inside a ForEach feedback loop or a solver. Now let's try to see some differences between the let's try to see the speed differences between all these setup. See the performance actually if this is slower than this one or not. Now I'm going to first calculate with the first loop, this one. And let's set the iterations to the same number for with the other one. Let's see. I want to go for the really big number, but not too big, so that my computer don't die. So 20. Let's see how much time it cost. Okay, it's a bit too much. Let's say 12. Still a lot of time happening. Okay, but yeah, that's too much. Let's say 11. And I'm gonna do with 11, and to calculate the performance, we can go to this performance monitor and click record. Okay, and then go back to the parameter and say 11 and see how much time it costs. Okay, now let's check the performance monitor and let's see how many seconds it costed. So it says in total 1779, so around 18 seconds to calculate 11 iterations. Okay, so let's remember this, 18. So let's clear this out, stop this, and go to the next one. This one right here. Okay, I'm gonna reset this to 1. Let me also reset this to something small. Okay, so for the nested loop, for feedback loop with a primitive wrangle, let's see how much time it cost with the 11 iterations. So I'm going to go to the performance monitor, click record, then set the iterations to 11, and that was really instant. Okay, if I look at the performance, it says that in overall it cost 0.16 seconds, so it's like 20 times faster. That's a vast. So you can see that you can already see the benefit of using this method. It's much faster than using like these. Might be easier to understand with these, but a bit complex, but by using primitive wrangle, because it runs simultaneously on each primitive, it runs much faster. Okay. Now let's try with the solver. The solver is a bit different in terms of the performance because it's calculating each step separately, so it might not be a good it might not relates to other like feedback loop iterations, but let's see. So if we want to do 11 iterations in total, we need to have like 220 frames, I think. So let's set the frames to 220, and let's run this until the end. So let's set the performance record on and go to the end. And that was also pretty fast. So if we go look at the overall speed, it's around 1.19. So it's around the same speed as the for feedback loop. Takes a little bit of time, additional time, because it's having a in between frames, which might cost a little bit of time. But overall, pretty much the same speed. So it also makes sense to use this method, solver with primitive wrangle. Okay, so let's reset the value and go to the next one, the final one, just using the code. Okay, so I have this number of iterations. Let's calculate the performance. Let's start recording the performance and set it to 11 and enable this. Now you can see that it's getting a time to calculate step. So let's see. Okay, now the calculation has been done, and let's see how many seconds it costed. So in overall, it cost 10.7 seconds. So it is a bit faster than using this method, but it's way slower than using a for feedback loop together with the primitive or solver. So still, I think it's not a good idea to use this method, but use it either a feedback loop with primitive wrangle or point wrangle or solver with those VEX. So only using the VEX might not be a good idea. Okay, so now that we understand the basic stuff, how we can implement this feedback loop or the recursions using feedback loop or solver, let's do more examples to get used to the process with the different geometry. Now, next example I would like to implement is the one called L system. And using this L system, I would like to create something like this, a tree-like structures. Now, L system is pretty much similar to what we have been doing, and it's just the name of the rule how you do the recursions. It's kind of a language system using those keywords like G, V, or W, or P to define the transformation process like move, scale, split, and so on. So having all these keywords with those operations, you can grammatically write some structures which could be defined as like a DNA of a final step, like these A, AB, ABA, and so on. So in this case, A becomes AB and B becomes A. So the first step, if we start from A, then A becomes AB. And in the next step, A becomes AB and B becomes A. So in total, we have ABA. And this continues to happen. So pretty similar to what we were doing for the geometry. The only difference is that based on the current conditions, the step will change. So if we have a longer length of the line, then make it much smaller, or at some conditions split it into two, and so on. So based on the current state, A or B change how it behaves on the next iterations, and that's how it works. By using this method, you'll be able to create kind of an organic like tree-like shape pretty easily. So that's what we would like to do in the next example. But before getting into it, let's do this with a really simple example, starting with a 2D fractal shape, 2D fractal tree-like shape. I am starting with a single point, which will be the starting point of the tree structures. So I'm going to create an add node at the center, 0, 0, 0. And I'm also going to create a group called end, which is going to be used to define which point should be used in the next iteration. So let's create a group for the point with an end. And let's also have some attribute which can be update it at each iterations. Since we're dealing with the tree-like structures, we want to define the angle for the branch and also the direction, probably the length. Maybe for the direction we can get it from the angle, so I'm just going to have the length of the branch and the angle of the branch. So attribute create, attribute create. I'm gonna create two attributes. One is the angle, and let's set it as a float starting from 0, and let's add another one which is the length of the branch, and as a point float, and starting from 0 as maybe starting from 1 for the branch length. Now I'm going to use the for each feedback loop, which is most handy to create the recursive. So I'm gonna create a for each number, change this to feedback loop by setting the for each end to feedback at each iterations, and for each begin I'm going to change this to fetch feedback. And to make it safe, I'm going to make the iterations smaller. It's always a good idea to start from small numbers, maybe 1. Now the process that I'm gonna do as an initial practice for analysis is pretty simple. First, starting from the single point, I'm going to create a 3 divided branch on 2D plane, having a same length and same divided angle. And in the second loop, I can create another branch, but having a smaller branch. Maybe it's using the same angle, like this. And keep doing it for each branch. Now in this case, I'm not really setting any conditions, so it's going to be really simple to implement L system tree. Now in terms of the implementation, what I have right now is the value called angle at each of the endpoint and the length. Okay, so let's say if I have an angle equal to 3 degrees and length equal to 1. Okay, and the first step that I'm going to do is I would like to create a 3 branch and a single point, and I'm going to use this angle as, maybe I should start from 0. Okay. Then I would like to use this angle as a starting angle direction for the center branch. If we have 3 branches, then this center branch will have this angle equal to 0. And by 0, I mean the angle between this vertical line and the branch. So if it's 0, then this direction is actually 0 degree. And the one that I want to create on the right hand side and the left hand side, I need to define another parameter. So let's say I have like branch angle equal to 30. So from the center, which is equal to 0, I'm going to rotate by 30 degrees to the right, 30 degrees to the left. And each of the line shares the same length, which is currently is equal to 1. And in the next step, I would like to multiply the length by 0.5 so that it will be half size smaller. So in the next loop, the size will be equal to 0.5. And for the angle, I would like to retrieve the angle of each of the current line. Okay, so meaning for each line I want to implement a different angle. For the center line, it's still on the center, so the angle between the vertical line and this center line is equal to 0, so the angle is equal to 0. For the right hand side, the angle is being rotated 30 degrees to the right, so let's say becomes 30. And this one becomes minus 30 on the left hand side. And doing the same step for this branch at this point right here in the second loop, what I want to do is to first create a center line which is using the same angle, which is equal to 30 degrees compared to the angle right here. Okay, and do the same thing to this direction and this direction. In this direction, the angle for the center line will be equal to 0. This one will be equal to minus 30. Now, we also want to rotate each of the branch to the right hand side and the left hand side by 30 degrees. So, in this case, rotate into the left hand side, which becomes 0. And if you rotate on the right hand side, this becomes 60 degrees. This one becomes minus 30 and 30, and this becomes minus 60 and 0, and so on. So keep track these angles for each line, for each branch, and the lengths will become smaller and smaller and smaller to create a pattern like these. And I am also would like to change this parameter, the branch angle, parametrically, so that I'll be able to control how far I want to open up the space between the branch. Now let's see how we can do this. In this case, I only want to access to the last point of the branch, so I'm going to use a point wrangle. I could still use a primitive wrangle if I'm iteratively creating a line as well, but either way is fine. I'm going to use the point wrangle, and let's set the group filter to end so that I can only control the endpoint. Now let's name this to branch, and let's try writing a code. First thing first, let's try to have all the necessary parameters. So first of all, I need to have a branch angle, so let's create a parameter called chf branch angle, and let's make the parameter as a degree, so I'm gonna set the minimum and maximum from 0 to 180 degrees, or maybe 120 degrees. Then change this to a radians from a degrees, so I'm just gonna do it right here. Convert this into a radians in order to use it for the rotation later. Now we also want to access to the angle attribute from the point and the length. We can just use it by saying f at ang, so I'm just gonna keep it as it is. Now since we want to create 3 branches for each point, I'm just gonna say for int I is equal to 0, I 3, and inside here I'm gonna create 3 points and together with the line. Okay, so first let's create a center line, shall we? So to do that, first I'm going to access to the angle and create a directional value to rotate the rotate the vector value, the directional vector value. So I currently, if I'm looking at these, the top direction is x. So I'm gonna use x as a original vertical line, a vertical like direction, and use the rotation to move the rotate the x direction on left side or right side to the right side. Okay, so first of all, I'm going to create a angle value, which can be derived from the current angle on a point. And let's assume I'm only trying to create a center line. I'm only trying to create a center branch. So I'm just going to create one single angle at this moment. And let's also create a base directional value, which in this case 1 0 0, an x directional unit vector. Now next thing I would like to do is to use the create a rotational matrix, starting by creating an identity matrix, rotate this by an angle using a 0 1 0, a rotational axis. Now, by having this rotational matrix, I would like to rotate this direction like this. Now, next thing I would like to do is to define the new length for the next step. So, but currently, I'll just use the current length, and when we go to the next step, next iterations, I'm going to set the length to the half size. So for now, let's keep it as it is. And what I'm going to do is to create a new position, which is going to be the current point position plus this directional value multiplied by the length, which is attached to this point with the end group. Okay, now the point has been moved, I think. Well, although we need to update the point positions. So we're not going to override at P, but instead we're going to create a new point and connect those previous point together with the new point to create the line as a branch. So int new pt is equal to add point at new positions. Now let's see, the branch angle is equal to 0, that's fine. Okay, one thing I was missing, if I look at the attribute create, I have set the initial angle to 1, which is wrong. I have to set the initial angle to 0 and the initial length to 1 instead. Okay, so going back to the code. Now let's see if I have this length applied to a point. So I have length 1.0, angle 0.0, and the group called end. Now by activating this wrangle, I can see that the point has been moved to the x direction by 1. And actually there are 3 points being created at the same positions, because I'm just using the single angle for all those 3 loops. So if I look at the result, I currently have 4 points, 1 point in the center and 3 points on the corner. Now let's also try to connect those points with the line. So int line is equal to add prim 0 polyline, connecting the current pt num, which has the end group, and the new point. Now's the time I would like to introduce this branch angle. I want to use this branch angle to rotate this center line to the left and the right. So I'm going to use this I value to modify this angle. To do that, I'm gonna start by a negative branch angle, and then create an addition I multiplied by branch angle, and plus the original current angle. So when the I is equal to 0, then this will be deleted, so you have minus, let's say, 30 degrees. If it's I is equal to 1, then this one becomes 0, so you are left out with this angle. If I is equal to 2, then you have positive branch angle, so probably in this case 30 degrees. So you have minus 30, 0, and 30 degrees out of this for each loop. If we go for each loop, and as a result, you'll be able to create 3 branch like this. So let's set the angle to 30, and you can see that it's happening like this. Now this is just a one step, and in the next step what I would like to do is to pick the end point and use it to be the starting point for the next branching. So to do that, we need to set the group at the end for each of the line. So, and remove the end group from the previous point. And also apply the length, the new length, and the new angle to each of the point. So that can be used for the next step. So we're gonna do it on the last of this loop. First of all, set point group 0. I'm going to set this end group to the new point with 1. And we also want to remove the point group end from the current ptnum, which in this case we don't have to do it inside the loop, but can be done outside the loop because there's only one point I'm accessing, and with this point wrangle. So something like this. And we also want to apply the new length and the new angle to each of the point. So set point at rev 0, length at new point, and can be a current length multiplied by 0.5 if you want to make it a half size in the next iterations. And another things, angle, so add point, set point at rev 0 ang, new point. Now you can refer to the current angle, or you can actually just say this current angle be the angle that I've just created right here be the center angle for the next iterations. So I can just say A right here. Okay, as a result, by leaving the loop, you'll be able to easily create this kind of tree-like shape. At each iterations, the size of the line has been scaled down by 0.5, and using the angle at each branch, it's changing its direction. And what's interesting about this shape is that if we increase the iterations to really big, like 10, and if we change this branch angle to 120, it looks similar to the one that we were doing, Sierpinski Triangle. If we look at the detail, it's a bit different, but overall, if we look from the far away, it looks like a similar fractal shape. If we have less iterations, it start to see less triangles, but having tons of iterations, you start to see this fractal shape, which is pretty interesting. Okay, now I consider this as a 2D simple practice, and by understanding this process, I'm going to make a 3-dimensional and more organic like shape. So let's do this next. Now let's think about how we can implement the 3-dimensional tree using our system. So I'm gonna start by creating a single line like this in 3 dimension. Okay, in y direction, and at the end of the point, at the end of the line, I'm going to create a branch, maybe 3 or 4, let's say 3, like this, but in 3-dimensional. So if you look from the top, it looks like this. So this is the center core, the center trunk, and you have 120 degrees rotated for each branch. Or maybe you can randomize it to make it a bit more organic. Maybe we can try that as well. And after rotating like this, at the end of the line, you do the same thing over and over again. So in this case, if you look from the top, it looks like these. And we're going to introduce some conditions to this one, like when to stop the recursion. I'm not going to, in this case, I'm not going to use the number of the iterations to stop, but I'm going to define when to stop this whole iterations or some of the iterations based on the length of the branch. So when the length of the branch becomes small enough, then that's when you want to stop this process. So I'm going to introduce some conditions how you can do that. And probably I could add some another random related values for the rotational angle or the timing when to stop the creating the additional branches. That might also be interesting. So let's also try to do that as well. Okay, so keep that in mind. Let's try to create this using a ForEach solver, a ForEach loop together with a VEX. In this case, I'm gonna try using a primitive wrangle. Now let's start by creating a line going upward in y direction. So I'm gonna create a line, and the default value is facing upward to the y direction with the length is equal to 1. So I'm gonna start with these default setup as a starting point. Now, since I would like to use the primitive wrangle inside a ForEach feedback loop, I would like to use a primitive wrangle to access the last created branches. So to do that, I am going to apply a primitive group called last, so that only the primitive which is in this last group will be controlled or used for the next iterations. Okay, initially there's only one line, so I'm just going to apply this group to this line. Now, next thing, what I would like to have is to some informations in order to rotate this line by a specified angle. In this case, an angle for the branch. Okay, which in this case I would like to rotate in this direction by some angle. And after I have rotated this wrangle, let's say 30 degrees, then I have this one rotated line. And the next thing I would like to do is to do a second rotation for this rotated line. Let me show you what I mean. So first rotation, what I want to do is to use do a rotation like this, and then the next rotation, what I want to do is to create do it for the branching. So if I want to have 4 branches, then I have to do like a 4 number of loops rotating 90 degrees for each step, using, in this case, y-axis. So I can multiply this by the tail x into the iteration value from the count 6, which is this one, this node. This node has a detail attribute called iterations. So I'm going to access it and multiply it with 90 degrees. Okay, probably didn't really get what I wanted. So let me check. For each begin, no, not begin, but count. Should be count. Alright. Okay, so this is what I want out of these single line before rotation. And I want to move this whole rotated branches upward, so that by having the previous branch and the next iteration, oops, not this one, but this one, I'll be able to have this single branch set. Okay, and probably I would like to set make the branch smaller by making it smaller like these. So what I want to do is to do this repeatedly, recursively, over and over again, and also use the direction of each branch as a new axis to rotate the branches. Okay, so consider that. Let's do it in a feedback loop together with the primitive wrangle. Okay, go back to the single line. And in order to do it, first we need to define the branch angle and also the axis in which direction by which direction we want to use it for the rotational axis to rotate this single branch, single line. So as initial axis, rotational axis, I'm going to say the x direction is going to be the axis to rotate this line, either left direction or either counterclockwise or clockwise. So I'm going to create an attribute create and apply that information to a primitive. So this should be a primitive class as a vector, and let's say the value is 1, 0, 0 as an axis, and the name I'm gonna say axis. Maybe I should say horizontal axis, because I also has this vertical axis, which is going to be the direction from the first point to the second point of this line. So it's going to be the v-axis, the vertical axis, and the one that I'm using, that I've just created right here, is the horizontal axis to rotate this angle, to rotate this line. Okay, now I think I have enough information to start off. Let's create a feedback loop. So for each number, and like I do for all the other set. I'm going to change this to feedback each iterations for each end, and set this to each feedback for each begin. Now I am going to create a primitive wrangle, and let's name this branching tree, and start writing some code. Now, first off, let's try to have all the parameters that I could use to control the tree shape. So, first of all, the branch angle. So I'm gonna create a branch angle as a parameter, chf branch angle, which could be a degree, so I'm going to convert it into a radians, just like I did with the previous example. Let's have this range between 0 to 100, maybe 90 degrees, or 120 degrees. Okay. Now let's also define how much you want to scale down the length of the branch at each iterations. In previous example, I have set as a constant value 0.5, so making it half size at each iterations. Let's say I want to control that as well, so I'm gonna say length ratio is equal to chf length ratio. Same for the angle, we can control how much the angle will decrease, or in this case could also increase. So let's also try to introduce a angle ratio. Ratio. Okay. Now, as I said, in this case, I want to stop this for each iterations when the branch length is small enough. If it goes if it's too close to 0, then there is no meaning to continue doing the process because we cannot really see the result. So I'm gonna create some additional parameter like small, the minimum length, and if the branch becomes smaller than this minimum length, then that's the condition when you want to stop doing the loop. So instead of using the number of iterations, setting the number of iterations, I'm using this conditional value to stop the loop, which might make sense a lot because you don't have to do like unnecessary loops anymore with these visually. Okay, and probably you can do the same thing for the angle, but I'm just gonna leave it with the minimum length. Okay, now other parameter that I could think of is how many like branches you want to create at each iterations. So let's say I'm gonna create a integer value, chi div, and by using this integer value, I would like to control how many branches I want to create at each iterations. Okay, and that's probably it, I think. Now, if you want to if you want to make it more organic in terms of the final output, it might be also a good idea to introduce some random values. So I'm gonna create some seed value just in case I want to create some randomness, and I'm gonna make it as a float value. Okay, now I think I have all the necessary parameters. Let's try to set some initial values. So for the branch angle, I'm gonna stop by 60. The length ratio, I'm gonna say 0.8. The angle ratio, 0.8 as well. The minimum length, let's say 0.01. And the division, let's say I want to split into 4 branches at each iterations. For the seed, it can be any numbers. Now that I have those informations, let's try to write some code. The first thing I would like to get is the the point position from this primitive which have the group called last. So I'm going to filter this primitive wrangle with last, then get the point number list to retrieve the first point and the end point. To do that, we can use the function called prim points at primnum. The first point will be the the starting point, which is at PTS0. Let's call this PTS. And the endpoint PTE is equal to the second point of this PTS. Since we know that there's only 2 points in the primitive. Okay, I think I cannot use PTS because it's already taken, so I'm just going to call it PT1 and PT2 to make it simple. Okay, now I also want to retrieve the point position as value as a vector, so that I can also calculate the axis, the vertical axis direction. So vector pos1 is equal to 0.0 p at pt1. Vector pos2 is equal to 0.0 p pt2. Okay, now I am also going to create a vertical axis value. So v axis is equal to position 2 minus position 1. So that's the directional value going from the first point to the second point. And since I would like to use it as an axis, I'm going to normalize it to make it as a unit vector. Now as an initial value, I already have this length. I can estimate the length of this line by calculating the distance between the starting point and the end point. So let's also calculate the length. The length is equal to distance between the position 1 and position 2. Now let's also retrieve the horizontal axis from this primitive as an attribute, which I have applied right here. So I'm going to say somewhere after v-axis, vector h-axis is equal to v at h-axis. Okay, so I think I have enough information to start creating some first step iteration, a first step process. So let's do this. So first thing I would like to do is to rotate this line. Rotate this line using this h-axis as a rotational axis by an angle of this branch angle. So just like we did previously, I'm going to first create a matrix starting with an identity matrix and rotate this identity matrix by an angle, branch angle. Then using h-axis, horizontal axis as a rotational axis. Now that I have a rotational matrix, I can now rotate this point positions right here at the end with the branch angle. Now to do that, we need to rotate this one position 2, but we also need to consider the pivot of this rotation. Like, what's the center point of this rotation? Where's the center point of this rotation? And in this case, position 1 is the center point of this rotation, which is going to be the pivot. Now currently it's at 0, 0, 0, so it doesn't really matter, but when the loop when we do the iterative loop and the next iterations, the starting point comes somewhere around here, so that's when you want to consider this position 1 as a pivot position. So to consider, we first need to move this position 2, which is the end point right here, subtracted by a position 1, which is going to be the pivot position. Now the whole geometry will be set on the 0. The starting point will always be at the center of 0, 0, 0. Then you can start rotating, and if necessary, you can make it back to the original position by adding the pivot. So after you have moved this endpoint together with the pivot, I am going to rotate this position 2 by multiplying this rotational matrix. Okay, now that I have rotated this position 2, I am going to add this pivot position so that it comes to the original positions. And then also I would like to move this whole positions with this directional value right here, going from the position 1 to position 2. Okay, so in that case, what I need to do is position 2 minus position 1. And by doing that, you can delete this position 1 with these equations, and you are left out with just position 2, which is the endpoint. Now, I think I cannot really add this position 2 because this is the rotated value. Actually, the rotated value, so I shouldn't add it like these, but I think I should introduce the new position, which is the copy of position 2, and I should actually rotate that new position instead of updating the position 2 like this. And the new position will be updated like this. Now let's try adding a new point as a point geometry using add point at new position and see where that goes. Okay, right here. And it is actually a 60 degrees rotated using x-axis. So in this case, this is in a rotation axis, and the line has been rotated clockwise by 60 degrees. Like this, you can see it. Now, next thing I would like to do is since currently the length of the line is equal to this branch right here, so I also want to control the length. I want to decrease the length based on this length ratio. So to do that, what I can do is to after I have rotated with this matrix, I can also multiply with this scale length ratio, and that will reduce the size by, in this case, 80%. If I make it smaller, I can increase more. I'm gonna keep it as something 0.85 for this length ratio. Now, next thing I would like to do is to connect this endpoint of the previous line together with the new point so that I can create the line. So int new line is equal to add prim 0 as a polyline connecting two point numbers. One is the 0.2, the endpoint number right here, so that is 0.2 pt2, and the new point is this pt. Maybe I should call new pt. Like this. Now I have just created a single branch out of the previous previous line. Now I also want to do, and the next step is to have a bunch of branches by rotating this single branch using this vertical line as an axis by a number of divisions. Now currently I have value equal to 4, so I want to have 4 branches for this line here. So let's try to do this. So to do that, I am going to create a loop. Maybe beforehand somewhere around here. So this is where I have created this directional value here, or maybe here, probably it's a good idea to do it right after I have scaled down the line, which the position is currently somewhere around here. And by adding the position endpoint, then it becomes bringed up back to right here. So I'm gonna create a for loop before we move the position to upward by a number of division. And first thing I would like to do is to create an angle value for each iterations. So in this case, in the end I want to rotate in total 360 degrees. So let's say V_ang is equal to, first of all, I'm gonna start by calculating the 360 degrees, which is equivalent to pi multiplied by 2. Then I'm going to divide this value by the division, which in result you get 90 degrees in this case if the division is equal to 4. So which means pi multiplied by 0.5. Okay. Now after I have that value, I can multiply by I so that each iterations you can get the V angle as the multiplication of 90 degrees. So starting from 0, in the next iterations you get 90 degrees, in the next iterations you have 180 degrees, and the last iterations you get 270 degrees in radians in this case. Now that we have an angle, we can create an additional rotational matrix to rotate this line. So matrix mat2 and do the rotation for this matrix with this angle that I've just created using a v-axis that I have created previously, connecting the first point and the second point of the previous line. Okay, which is this one right here. Okay, now that I have created the matrix, what I'm going to do next is to rotate this end positions right here. Okay, so to do that, I think it's not a good idea to update this end position as it is. So in here inside the loop, I'm going to create another vector to copy this value so that we can separate the operation. So I'm gonna say and pos 2 is equal and pos. Okay, and what I'm gonna do here is to update this end pos 2 by rotating by this matrix 90 degrees at each iterations. Now that I have this updated positions, what I want to do is to do the same operations that I did here. I'm just going to cut and paste it right here and rename this endpos to endpos 2 and do the same things for these. I'm gonna bring this up right here and the new point should become endpos 2, and that's probably it, and you'll be able to create this branch as a result. So this is going to be the first step. And by changing the branch angle and the length ratio, you'll be able to see what you can control inside the first loop. Okay, and this one as well. By increasing the divisions, you can increase how many branches you want at each iterations. Now, by creating a line like we were doing for the other examples, we need to apply this last group to this newly created line and remove the last group from the previous line. So I'm gonna say set prim group 0 last to this new line, and for those previous primitives, I'm gonna say set prim group 0 last at current primitive, which is at prim num to 0. And let me make sure that I'm starting with small number of iterations, starting with 1. And if I check the geometry spreadsheet for the primitive that I've just created, I can see that I see 4 primitive with last group and 1 primitive with a last group equal to 0. And I can also see that the new line that just has been created doesn't have any horizontal axis, so we also need to apply this horizontal axis as well. And this is where we want to be careful. We cannot just pass this horizontal axis as it is, because currently it is x direction value 1, 0, 0. And if we just try to pass this as it is to the new line as an attribute, let's see what happens. Set prim attriv 0, h-axis, new line. If we just pass this h-axis as it is from the previous line, what we're gonna have when we increase the iterations, we see actually doesn't really look bad. If we increase the iterations, now theoretically has to be symmetrical, but you can see that at some part is trying to see some differences in the x and z direction. Now that is because the rotational axis for the first iterations is always equal to x direction, and that makes the rotation a bit skewed. So if you want to have like a symmetrical geometry as the final geometry, then you also need to consider the change of this horizontal axis. So what I mean is that you also need to rotate this h-axis when you have rotated the line inside this loop right here. I have used the matrix 2 to rotate the branches, and just like we did for just like I rotated these lines with these matrix, I also need to rotate this h-axis using the same method, using the same matrix. So what I just need to do here is to somewhere around here, I'm going to create a new horizontal axis. Let's name this vector, or maybe somewhere after I have updated the npos2, I'm going to create a new horizontal axis, which is the copy of the current h-axis. And then what I'm going to do, I'm going to rotate this h-axis with matrix 2. And I'm going to bring this new h-axis as a next horizontal axis. And as a result, you'll be able to have a symmetrical shape. And now you don't see any size differences in any directions, like this. Right? Now, so far so good. The next thing I would like to do is to create a condition when to stop these iterations by checking the length of the current line and stop when the branch length is small enough. This is the minimum length that I'm going to use to check its length. maybe 0.01 is too small. I'm gonna set it to 0.1. I can check whether I should stop this operations somewhere when I have get the current length of the line. So somewhere around here. This is where I'm getting the current length, and I can check here if this current length is smaller than this minimum length or not. So let's say if this length is smaller than minimum length, and that's when I want to stop operating this process. So I can say just return. Return will just skip all the rest of the code afterwards and just leaves this process. Now let's test this out. I'm going to reduce the number of branches a little bit so that I can test it out clearly. Now let's try to increase the for each iterations somewhere around 10. Maybe you can see a bunch of lines too much, so I'm gonna reduce the length ratio as well to 0.8. Okay, now you can start to see that after a while, maybe it's still too big. Maybe I can reduce the length ratio to 0.7. Okay, now you can see that after iteration 6 or 7, the process just stops because the length of the branch is now too small to operate because it's smaller than 0.1. Now it doesn't move anymore. So this makes more sense. So that even though we have a high number of values right here, let's say 100, it's just stop as soon as the length becomes too small. So we don't have to do the unnecessary additional calculations. Now let's introduce some other parameters which we didn't really use it yet. So I'm going to make this length ratio back to 8. Okay, and the next value that I would like to use is the angle ratio. So control the angle through each iterations. So in this case, I'm reducing the angle by 0.8, meaning 80% at each iterations. And to do that, I do need to have this branch angle applied as an attribute so that I can recursively refer to it. So to do that, we can go back to this attribute create to apply an additional attribute to each of the primitive, which is a branch angle. Let's do that. I'm going to create a new attribute. I'm going to say angle as a primitive float, starting with, let's say 0. It's fine. Or maybe I can, instead of setting the angle right here, I can set an attribute right here. So I'm gonna say, let's say 30 something, or 60. Let's say 60. And probably might be a good idea to make this as a slider so you can create an additional float value as a slider somewhere around here with an angle between 0 to 120, and copy this value to right here. So that you'll be able to control it with the slider here. Now in this case, I don't really need this branch angle inside this triangle anymore, so I'm gonna delete that. And remove this one right here. But instead, I'm going to retrieve the branch angle from the a float attribute. So ang, since this is the degrees, I'm going to convert it into radians, like this. Okay, now for the branch angle, I want to change its ratio, change its size, change its value based on this ratio for the next iterations. So what I'm going to do is to update this angle, apply to the primitive by saying set prim additive 0, and for the new line is the current branch angle multiplied by the angle ratio. Now one thing I forgot to do is to when we update this angle attribute, we actually need to apply it as a degrees instead of radians. So I'm going to convert this back into degrees by using degrees functions. Like this. Now the update has been done, and if we try to change this angle ratio, you can see that each iterations, if we make this angle ratio small, then at each iterations the angle becomes smaller and smaller. And if we try to have more branches, would have this kind of fractal-like shape, which could be interesting, like this. Combining with the lengths, you can start to see more organic shapes happening. Now as a final step, I would like to use this seed value so that I can use some random related values for several purposes. One of the purpose I could use this randomness is to change the angle of this branching to make it a bit more organic. Now there are two places I'm using angle. One is to use it with the horizontal axis, and one is with this vertical axis. Let's start by changing the first angle for the matrix 1, this first rotational matrix, where I'm using this branch angle as it is. So let's try to modify this one. So to do that, I am going to introduce some random angle first. Let's say the random angle is in between minus 30 degrees to 30 degrees in range. So to do that, to create that, first I'm going to create a random value which is in between 0 to 1 using this seed value. Maybe based on the primitive number as well, so multiply by the prim num, and also add some constant value to make it more organic. Okay, now this is the value in between 0 to 1, and I would like to convert it into in between minus 30 degrees to 30 degrees. So I'm going to create some other values like range, let's say 30, and convert it into radians. And then I can update this angle by using the fit function, fit 0, 1, to fit between the minus range to positive range. Now let's also call this random angle, rand angle. And what I'm going to do is to just add this random angle to the branch angle and see what happens. Okay, forgot to say rand angle. Now as you can see, each branch start to have more randomly random horizontally rotated angle start to become more organic. And probably I could parameterize this value here. So let's say random h angle as a degrees. So I'm going to make this range from 0 to 120. If I increase this, let's see, it starts to see more randomness start to happen, makes it more organic. Okay, now I can also introduce the second random rotation, which is for this b-axis, which is inside this for loop for the matrix 2. It's this one. So let's also try to have some random value for this one. So to do that, I am going to again create some randomness. I'm just gonna copy these, set, place it somewhere on here, and I'm gonna call this random v angle, and gonna call this range 2 random angle 2, like these, and just change this constant value to something different so that you can get the different result. Then I am going to add this random angle to this b angle. Okay, let's promote this random v angle. Let's also set the range between 0 to 120 and see what happens. If I increase this, okay, nothing really happens. Maybe I'm doing something wrong here. Okay, actually I have to change this range 2 to range 2 as well. Okay, now I start to see some changes, start to see some rotational offset. You can see this. Now I kind of see that each branch is rotating at the same speed, so it's not as I intended. That is because this is inside this another loop here, and it's for each primitive I'm creating a number of divisions, number of divided branches. So I think I also need to use this I for the random seed. So what I'm gonna do, I'm going to add I multiplied by some other values for additional seed value, and that should create more randomness like this. So combining this random v angle and random h angle, you'll be able to create more organic stuff to happen. Okay, and you can also increase the divisions to make it more dense. Maybe I can reduce the length ratio. Oops, that was too big. Probably somewhere around here, which creates a nice tree-like feeling. Right. It's like this. And I can also control the maximum angle, the angle ratio, and so on. This is one of the way you can create a three-dimensional L-tree branch, L-tree tree-like geometry using a similar method that we were doing, but with more complexity. Now, if you want to make it as a polygonal geometry, what I would do, I might want to start from the thick trunk, then make those branches thinner and thinner based on the lengths of this branches. So how I can do that? Let's see. So to do that, what I could think of. Okay, this might, let me just see what's the best shape I could think of. Let me go back to this one, starting somewhere around here. Looks nice. Yeah. Okay, so let's see if we want to. So let me increase this angle a little bit more. So let's say if I want to like make this a tree curve as a polygon. Okay. And to do that, I'm going to use the node like polywire, and you can read the point attribute using this polywire for a wire radius. So what I'm going to do is to set a scale or the thickness at each point so that I can control the thickness at each branch. So to do that, I am going to introduce additional attribute to make it as a thickness. So going back to a create attribute, I'm going to create an additional attribute called thickness, starting from 1. Okay, for in this case point, because I need to access to a point attribute in order to use it with the polywire. Now going back to the branching tree, what I want to do is to update this p scale, the thickness, and make it smaller and smaller based on the iterations. So in the last, somewhere around here, I have created the new point right here. So this is the point where I want to update the attribute for the thickness. So let's say set point attrib 0 thickness at new pt. So currently it's equal to 1. So I'm going to refer to the current thickness value, which can be retrieved from one of the point. Maybe I can refer from the point 2. So float current thickness is equal to point thickness at pt2. Okay, now for the new point, what I'm gonna do is to multiply this thickness by the length ratio, which I have used to smallen to make the length of the branch smaller. At the same time, I'm going to make this thickness smaller with this using the same ratio. And as a result, when you leave the loop, you'll be able to get each point with different thickness become smaller and smaller based on the branch size. Now, having those values, I can go back to this polywire and accessing to that attribute. So at thickness, initially that was too thick, so let's multiply it by 0.1, see what happens, and now it looks much better. Start from a thick trunk and starting to create more thinner and thinner branches like these. Looks like a blockly. Now if I increase the little bit of divisions, it becomes more smoother. Like this. So this could be one of the way to control the to create a polygon. Now based on those the thickness, I can also colorize it, the point. So let's say I want to access to this thickness value for each point and make this color going from brown to green. Now it's the other way around. Okay, now the coloring doesn't really look good, but you see what I mean by this. Okay, so if you want to polygonize this, this is one of the way you can do. Looks nice. Now you can also create this the same things using a solver as an animation. And like I said, you can just replace this whole feedback loop with the solver, and inside of solver you can just place this branching tree. But there is one downside using just replacing the solver, because as a result you get as an animation is this kind of a blocky animation, like from the single branch to the next branch it just goes straight straight ahead to the next branch, just creating instantly. But actually as an animation, probably the things that you really want is kind of a smooth animation growing from this very start, slowly start glowing and slowly creating the branches, like smooth animation. So that might be a bit of challenge, but let's try to think how we can do that using pretty much the same method, replacing these as with solver, but what kind of additional things we need to do to create this kind of smooth animation. So first I'm just going to copy all the stuff that I have written here, like we were doing for any other solver based stuff. I'm just going to replace this feedback with a solver. So bring this right here, bring this here. I'm just gonna copy this one, or cut it. Copy this one and go inside the solver and connect it to this previous frame. And we can now delete these and see what happens. Now let's make it go slower one by one. If we go to the next frame, let me just have 20 frames maximum. So currently at each frame the branch just grows instantly. Now just like we did for the other solver examples, somewhere around here we could also introduce this switch, but it still gives you like an instant like step from one branch to another. But let me just copy the switch node and go back to this new solver, apply it right here. Now make this whole frame back to 240. Now let's see what happens. So by each 20 frames the branch grows, but like it just instantly. So in order to make it smooth, what I could do is going inside this solver, and within 0 to 20 frame, or 20 to 40 frame, or 40 to 60 frame, I would like to control the length of this curve, this line with the last group with some ratio. In this case, I could use a node something like carve. Okay, and first thing I would like to do is to make this curve only affected by the last group. Okay, and let's see what it does. So what it does is trimming. If I change this first hue, it's trimmed from the first point, which it's not the one that I want. If I use the second hue, So this one trims the curve from the first to end by setting from 0 to 1. Okay, so what I could think of is to control this value based on the frame value. Just like I did for this switch, I'm going to make this value going from 0 to 1 based on the frame goes from 1 to 20. Okay, so if the frame is equal to 20, that's when the new branch is going to born. So what I could say here, first of all, I am going to divide the current frame by 20, which will create, first of all, I can get the the modulus, get the remains of frame when divided by 20. Now that will give you a value in between 0 to 19. Now I can divide that with 20. Will give you a value in between 0 to 1. Like this. Going from, at each 20 frame, it grows from 0 to 1. So by introducing a parameter like these, if I go back upward and play it, okay, nothing things to happen. Let me go back here. Okay, thing is, I think I need to change the timing a little bit, because when it becomes 20, this becomes equal to 1, and when it becomes 20, that's the timing when I want to have this value to be equal to 1. So what I could do, I can say f plus 1 and see what happens. Okay, one thing I was missing, I shouldn't do it right here, but I should do it around here. Actually, I cannot do this way as well, because this is a feedback loop. So if I make it smaller than in the next iterations, I'm using the smaller branches to activate this branch. So I should make this bring upward somewhere around here. This should, I think this could work. Let's see. So if I play it now I do see some glitches, so that is because of these values. If I make this f, now it's better. Now you can see more desirable animation. So I didn't touch anything inside the solver, just that I have this switch, but just outside of solver I have added this curve together with these expressions using the same frame values that I have set for the switch to make this smoothly growing animation. Now at some point I'm having this back and forth when the growth just finishes. So I think I need to set some conditions when I should stop this curve. That is related to when this branch stops. Okay. So as soon as it stops, I think I need to set this primitive grouped last to 0. So which is not done when I do the return. So maybe I can bring this before the return so that every primitive that has run through this code will lost its last group. Okay, now let's see what happens. Going back, reset, play. And there you go. Okay, now if I try to show it with the polygon, looks like these. Nice. Nicely animated with these polygon. Maybe it's getting heavy. It looks promising. Alright, so that is the way to create a L3 branching tree with an animated options with the solver. Now in the last example, I would like to introduce how you can use this recursion technique to create a subdivision. And in this case, I'm just going to try to create a 2D subdivisions for a plane. Like I show in the image, I'm going to split the square into a 2 by introducing a single line horizontally at random vertical positions, and on the second loop I'm going to cut those 2 squares into 2 by having a two vertical lines at random positions, and continue doing it until you have a bunch of random boxes or random squares, random rectangles, I mean. And to make it a bit more fun, I'm going to also try to animate those splitted rectangle going up and down, left and right, and so on. And that will be the final example that I'm going to show how you can use the recursive for the other purposes. Now, let's start by creating the initial setup. I'm going to start by creating a grid with no seams. So grid, and I'm going to change the shading to smooth wire shaded. I'm going to change the rows and columns to 2 by 2, but there is only 4 points in total to express this square at this moment. Now what I would like to do is to first create a horizontal line somewhere in the random positions, and then in the next iterations I want to create this vertical line at random positions. So the direction will be horizontal, vertical, and so on. So the direction switches from 0 to 1 to 0 to 1, like that, like a switch. So I'm going to have this switching related attribute as an attribute to this primitive. So I'm going to create a primitive wrangle, or I can say attribute create, and let's call the attribute name SW for switch, and for each primitive as an integer starting with 0. So let's say if the switch is equal to 0, then I'm gonna go for horizontal direction. In this case, maybe a x direction. And if it's equal to 1, then goes for a z direction. It's a vertical direction. Alright, now this is for the initial setup. I'm going to now create a feedback loop. Okay, and I'm going to try to create an animation without using a solver in this case. So I'm going to create a procedural animation by using the frame value together with this ForEach solver, and see how we can do that. Okay, now first of all we need to change this gather method to feedback each iteration. And for each begin, I'm going to change this to fetch feedback. Now go inside this one. What I first want to have is the square, which is and the point number, which is sorted out by a sorted out by clockwise order. Now currently if I check the order of the point, it says 0, 1, 2, 3. So you can see that the point order, it just goes diagonally from 1 to 2. which I don't really want, but I want the order to be 0, 1, 2, 3, like a clockwise order. So to have that kind of order, I'm going to use the sort node and change it to a point sort by vertex order. By doing that, you'll be able to have this clockwise point order going from 0, 1, 2, 3. And this is pretty convenient in order to define and which edge you want to pick, either from 0, 1 or 1, 2. Then I can say which ones can be for the horizontal split, which ones for the vertical split, and so on. I am going to use a primitive wrangle in order to split the square. And in this case, I am not going to apply any group. That is because I am going to like split every single squares at each frame. So in the first frame, I have one square, so I'm going to split it into two. You have two squares being produced. Now for the next step, I'm going to split each of the primitive by 2, so 2 by 2 you get 4, and doing it for each primitive each iterations. So the number of the primitive will be increased by the multiplication of 2. Okay, so by understanding that, let's go to create this square subdivision. Now, since I'm going to try to use the random value, it might be a good idea to have this random seed number for each iterations for this feedback loop, which can be accessed from this for each count. If you look at the detail attribute, there's a value co-iterations, and this can be used for a random seed, I think. So let's try to access it by connecting this for each count to a second input of the square subdivision, a primitive wrangle. And let's try to get the iteration value. So iteration is equal to detail from the second input called iteration. Now I also want to get the point array from this primitive. So int pts array is equal to prim points 0 at p prim num. Now, as I said, for each step, for each iteration, I want to make this switch attribute to become 1 when previously it was 0, and make it 0 if it's equal to 1. So to do that, I'm going to create a variable called SW and access to a current switch value. Now by subtracting by 1, you'll be able to switch between 0 to 1 at each operation. So if it's 0, then you get 1. If it's 1, you get 0, and so on. Now next thing I would like to do is to define in which position I want to create a split horizontal line or vertical line. And I would like to define its positions by the ratio in the value in between 0 to 1, starting from the starting point. So if the value is 0.5, then that's the middle position. If it's 0.1, it's somewhere around here, 10% from the start to end. Now if the value is too small, then I'm going to start to have really thin shapes, so I might want to reduce having too small values. Okay, so let's also try to reduce that by setting the minimum and maximum value. Okay, so first of all, I'm going to create a random seed value for the random value. So float seed is equal to some parameter that I can define myself. And I also would like to change this value based on the iteration. So let's add it with an iteration multiplied by some custom number. And probably I would also want to change this value based on the number of primitive. So also add a number primitive multiplied by some custom value. And this is I think it's a good idea to have a random seed value. Okay. So by having the seed value, I'm going to create a random value using rand with the seed. And this value is going to be in between 0 to 1. Now, let's say I don't want to have I don't want to have this mesh geometry, the mesh shape, to be in less than 20%. So let's give another parameter. Let's say min size or min scale. CHF min scale, and let's set the minimum scale to 0.2. Okay, and what I'm gonna do is to update this random value by using a fit function, so that the random value will always in between 0.2 to 1.0 minus 0.2, which in this case I have this parameter, so let's replace this. Okay, so then now the value is in between 0.2 to 0.8. Now we can try to use this random value to define where the position should be for the split. If SW is equal to 0, I'm going to choose one of the point from here. If SW is equal to 1, then I'm going to choose one of the point inside this edge, on top of this edge. All right. Now, in order to split this square just inside the VEX, you need to create 2 points, one on the one of the edge and one on the other edge, in the same perpendicular positions. So to do that, let's create a loop of 2. Okay. And by adding 2 points, we also need to create 2 primitive, one at the right hand side, one at the left hand side, and also we do need to remove the original primitive. So let's remove the original primitive on the last remove prim 0 prim num. And let's also create a new primitive inside a loop, because we want to create 2 primitives. We can just create it inside this loop. So int new prim is equal to add prim 0 as a polygon. Currently we don't know where the position is, so I'm just going to create it as an empty value, empty primitive value. In order to create 2 points, just like I did for the Sierpinski triangle, we could use this random value right here as a scaling value to define it as a positions. So using one of the corner as a pivot, we can scale this rectangle or square by some ratio. Let's say this is 0.8, then you can scale this by 80%. Size will be something like this. And on the other side, on the other corner, we can scale this square by 100, subtracted by 80%, so 20% size, which is a result, which in result we could fit, or we could connect these two splitted rectangle together to keep the original square size. So that's what I would like to do here, and let's see how we can do this. Now in order to do that, we need to access all those 4 points at each iteration. So I'm going to create another loop accessing to all those points right here. So for int n is equal to 0, n is the length of PTS, and we're going to get the PT at PTS, and we're also going to get the position value. Pos is equal to 0.0 p at PT. Now we also want to get the corner point to use it as a pivot. So what I'm gonna get is the diagonal positional corner, one for at the point is equal to 0 and one at when the point is equal to 2. Okay, so let's get that vector. So one of the point I'm going to call it as opos point at PTS 0. For the other corner, when the point number is equal to 2, then I'm going to say mpos is equal to 0.0 p PTS 2. Based on this corner position as a pivot, I would like to scale each of the point. So to do that, I am going to create a directional value for O and M. In this case, I am going to subtract with the current point position with a opos. Okay, I think I have some errors somewhere. Remove them. Let's comment these out a little first. So let's assume that this opos is a point position somewhere around here, which is the PTS is the order is z equal to 0. So right here, and the position is the every corner point. So I'm calculating the directional value right here, going in into each point from the O positions. So from this point to here, from this point to here, and from this point to here. Okay, so I have 3 direction. Actually, I also have this direction from this position to this same positions. Now, what I would like to do is to use this vector value to scale these point either on x direction or z direction based on the switch value. So let's say if the switch value is equal to 0, then I want to move it in x direction. I want to scale it in x direction. Okay, so that means if we look at the 1, 2, or 3, we can access to this x value, the current x value, which is position.x. Actually, we can just refer to this O directional, the x coordinate of this O direction. So O direction.x determines the size on x direction compared from this positions. So if this is the old positions and this is the older positions, when it is here, the x directional value of this old direction is equal to 0 for this 3. For the 2 and 1, the value is equal to this length. Okay, so that's the position. So so this one is 0, so even if you multiply 0 with any other value, you get 0. But those value, when the point is equal to 1 or 2, then if you multiply by 0.5, then you can move this point with the half size to the right direction. So that's kind of a reason why we have this value here. So let's try to multiply this by the scale value that I've created, which is this random value. So rand val. Okay. And we also need to consider when the n is equal to when the I is equal to 0 or I is equal to 1. Because we are creating two squares. If we scale the first primitive to right direction, then we have to pick another corner to move it in the left direction. Now I'm gonna start by creating this first primitive. So I'm gonna say if I is equal to 0, then multiply the x coordinate of the all direction by the random value. And what I'm gonna do is to update the all direction x with this newly multiplied value. After leaving these conditions, I can now use this all directions for a new point positions. So let's see, then let's say new positions is equal to pos, which is this positions, plus this newly created all direction, newly updated all direction. And to make it as a geometrical change, we need to create a new point. So I'm going to create a new point by saying add point at new position. Now we also need to add it to a primitive that I've created right here. So after I have created the point, I'm going to add vertex to the prim, new prim with this new point. New prim. And let's add some random seed. Now we need to create another conditions when the switch is equal to 1. So when the switch is equal to 1, or I'll just say else, and if di is equal to 0, actually you also need to create the additional conditions to this one as well. So else and else. We'll keep that for a later update. We are just creating the one side of the geometry by just accessing to I equal to 0. Now in this case, we're going to use the z direction as a scaling value. So all direction dot z is equal to all direction dot z multiplied by a random value. Now as a result, some kind of geometry has been created. In this case, the switch was equal to 1, so the geometry has created in this way, in this side. Now I can try to remove the whole geometry by saying remove prim 1. Okay, now let's try to leave the plane. Now there's too much iterations right here happening, so let's start with a small number. Now this has created the primitive right here, and one of the primitive has kept the same size for the other side because I haven't set any conditions for I is equal to 1. So we need to do this as well. For this one, this is going to be a bit more simple. I'm just going to not that simple, I guess. We need to multiply the 1 minus random value for the other side, and we also need to pick the other corner, in this case a mpos. Okay, so let's do that. We're going to say we're going to also do the same things like we did right here. So vector m direction is equal to position minus npos, and npos dot x is equal to a m direction dot x multiplied by a 1.0 minus random value. Okay, and do the same things for here. I'm going to copy this one, replace it with z. I also need to change the position where I create these new positions. Currently it's only using old positions, but when the switch is equal to 1, then I want to, or I is equal to 1, then I want to use the m direction instead. So let's say I'm going to create a general direction previously, and then update the direction with the updated old direction or m direction, like this. Okay, now that I have only one general direction, I can replace this old direction with the general direction. And I think I still have some problem here. Let's fix this one. Okay, I need to change this opos as well. Okay, so let's create another general positions, general corner positions. I'm gonna call this cpos. Okay, starting from 0, 0, 0. And when the I is equal to 1, I'm going to update the cpos with a allpos, cpos with npos, cpos is equal to allpos, and cpos is equal to npos, and replace this allpos with a cpos. Now I think I still have some problem here. Let's see why. Okay, one mistake I made. It's not npos, but it has to be m direction. Right here and right here. Okay, now I was testing out by making this I equal to 0. Okay, now I think the object has been splitted correctly. Okay, so if I change this seed, I'm changing where to split this primitive. And this is for the first iterations. And if I increase the iterations in the next step, I'm hoping the other direction will be used. Okay, not. So something must be wrong. And that is because I didn't update the SW, the switch attribute, anywhere. So let's also add it as a primitive attribute. So going back to a primitive where I have created the primitive, which is this one right here. So I can create an attribute. I can set an attribute to this primitive, set attriv, set prim attriv. The name is SW with the current SW value. Okay, add the new prim. And let's see what happens with I increased the iteration. Now it happens what I wanted to have. So the first iterations you have this vertical line spread. In the second iterations you have the other directional split for each primitive, and the directional split on each of the primitive, so on and so on. Okay, that's good. Now this is kind of a static result right now by changing this random value, but I would also like to make this as a smooth moving animation. to make it a bit more interesting than the last. So to do that, I am going to use a additional noise value to use it with the frame value, where I can use that somewhere after I have created this random value here. Okay, since the random value is being fitted by 0.2, it's in between 0.2 to 0.8, I can add minus 0.2 to positive 0.2 so that it will be still within 0 to 1 range. So what I'm gonna do here is to try to create a animated noise value which is in between the range of negative 0.2 to positive 0.2, and use the frame value to animate it. Okay, so to do that, I'm going to add a noise related value, and probably referring to the current seed also makes sense, so I'm gonna add the seed plus the current frame value and multiply by some speed. Which should create a value in between 0 to 1, probably around 0.3 to 0.7. So let's fit this value so that the value will be in between the negative 0.2 to positive 0.2. In this case, the value comes from this min scale. So I can refer to this min scale minus min scale to positive min scale, and see what happens if I play it. If I play it, okay, nothing really happened. So let's see why. Okay, that is because I didn't set any speed. Currently it's 0, so I have to promote the speed. Set it to 1. Then if I play it, now it's too fast. If I make it 0.1, you start to see some animation happening. Cool. If I make it 0.15, maybe too fast, 0.05. Okay, it's interesting. Now I can also colorize each squares randomly. For each primitive, and let's see if what kind of attribute I have. Not real much, so I'm just gonna say random primitive. Okay, probably I could add some ID related attribute to each of the primitive and make it as a color related value. So what I'm going to do, I'm going to, let's say, first of all, use the sort to randomize its positions for the primitive, then get the ID for each primitive, or maybe based on the area might also work. So I'm going to calculate the area for each primitive, and let's also set the visualize range, go from 0 to 1, so that will be easier to use with a color angle, a color node. I'm going to connect with the area, and let's change the color, going from red, or just use the infrared. Okay, good. So This is another example using a recursion method to do the subdivision in this case. The same idea can be applied for many other purposes. For example, if you want to implement yourself like a cut mall subdivisions, which can be available by using the subdivide, you can also do that by yourself using the same principle. You do need a little bit of geometrical work like using a half edge and so on, but it's totally doable. Now this is it for today's sessions. We were talking about the recursion, how you can implement using Houdini by using a ForEach loop node, solver, and only VEX, together with several examples. The method shown here can be really generalized to use for many other purposes, and you do use a lot of recursions for many geometrical operations for algorithmic design for sure. So try to know its method, try to make it your blood so that you can always use it as a tool set. Now for the next topic for the VEX for Algorithmic Design tutorial series, I would like to talk about the basics of matrix version 2. Now I have already talked about the basics of matrix, like the addition, multiplication, together with the vectors and so on, like a rotational matrix and so on, in a episode 15, and where I taught the really real basics of the matrix. Now, having those informations, having those knowledge, I'm going to extend the idea a little bit and try to do more of with this matrix, what we can do with this matrix with several examples. So hopefully you'll have more understanding how matrix works and why you can really use it for many other purposes. Okay, this is it for today. Thank you very much for watching, and if you like the video, please like and subscribe the channel. I'm also doing the Patreon, so if you'd like to support me creating these videos, I would really appreciate it. You can go from the video description page for the Patreon page. You can also download the file that I've created today from the video description page, from the project file link. And you can also watch the other tutorial episode covering many other topics, and any comment is welcome. Okay, thank you very much, and see you next time. Bye.